105. Yeah, so it's recording. So the first thing that you see, this is from the home page, is this. This is the course, it describes the course. So we have the objective and the usual typical stuff. What you would need is to know is the homework, the exams, and the grading policy. So there will be 4 homework assignments. Each homework assignment will be worth 15 points. Okay, and there will be 2 tests. Each will be worth 40 points. The 2 together, so 20 points each. 15 points times 4 homework assignments, and 20 points times 2, there will be 2 exams. One will be the midterm and one will be the final. 20 and 20, and each homework is 15, right? So that makes 100. Now, this is how it will be. There will be 2 sections in this course which are pretty independent of one another. One is matrix methods, and the other one, section A is matrix methods, section B is convex optimization. And in each section, I'll try to put in a little deep learning or data science or some other interesting application to it. To make it interesting. So the midterm exam will cover section A, matrix method, and the final exam will cover section B, convex optimization. Okay, and each exam will have both an online quiz, 8 points, and a take-home test of 12 points. Okay, that's how I get the 20 points for each. 8 plus 12 equals 20. Okay. And so I have extensive lecture notes, so you don't really have to consult any outside resource, notation difference, blah, blah, blah. So I found that my lecture notes are enough, more than enough. Okay, and these are, so there will be 10 lectures for matrix methods, which is the first section, and 9 for the next section. And this is, I plan to cover this much before the spring break. And then right after you come back from the spring break, we will have the quiz for section A, that's a midterm. And then the final exam will be, again, both the midterm and final exam will also have a take-home portion. So I'll give that to you after you come back. Okay. I've left out some space in case I'm not able to make it, but otherwise, you'll ignore these 2 slots. Okay, one of the things that you should note here is that don't use webmail. I don't check webmail so frequently. The best place to ask a question is put it on the Canvas discussion. Okay, that way everyone else would be able to see how I've responded, and others can also be given a chance to respond. Okay, and if you need something personal, then you can send me a Canvas email. Okay, but not webmail. Classroom conduct this is the usual stuff, and note that if you use any outside resources, you're expected to work independently, but if you use ChatGPT or something, let me know. Put it as an acknowledgement in when you submit your homework. Now, this is something, these are all stuff that it's pretty standard. Okay, so this interactive tutorial session, this is for the benefit of mostly the distance students who might be out of touch with some of this, because you guys are in school, so you know all these things, but and you know enough MATLAB, but they might not. So I schedule special tutorial sessions on Saturdays or Sundays. I would prefer Saturdays if that's okay with you guys. Evenings so that everyone can participate. Okay, and and especially for the homework questions, I will give you tips of how to solve them. Okay. And the rest is just the usual stuff. Now, submission guidelines, I'm pretty strict about how the format in which you submit, because one thing is MATLAB code, sometimes when I read the MATLAB code and I'm able to see that it'll work. Okay, but sometimes I have to check if it works. Okay, so the PDF file itself, I'll just copy paste the MATLAB code. Okay, so one way to do it is just make everything look neat and presentable. Okay, and I strongly suggest that you use, instead of handwritten homework, you use Microsoft Word or LaTeX. And I'll tell you, it's much, it'll be easy for you to do the latter, use Microsoft Word or something, because, I'll tell you. Anyway, these are, you can go through all of these, and so this is acceptable presentation of the results. It's readable, right? This is not acceptable, MATLAB. Okay, so when you copy paste, make sure you align it like this. This is 1 point something e to the minus 5. So you see, these are not the way you should present your answers. And then especially when we're dealing with log matrices, see, it's so hard for me to read something like this. Right? This is a matrix. How on earth would I able to read this? I wouldn't, right? And in cases like this, in this course, it's the death penalty. No, but you know what I mean. Okay, so these are examples of acceptable and unacceptable. Okay, so just go through it. Okay, so now I told you that we have extensive lecture notes on everything. So section A, these are the lecture notes. How many pages? 75 pages. All written by me. Okay, actually there's a lot more than 75 pages. I deleted the ones, I'll be adding some more stuff, and the ones that we won't cover, I'll delete. Probably be covering it. Well, I'll just keep them for your reference, but. Okay, so might not be able to teach graph Laplacians. I'll teach something else though this time. Okay, so this is sample of the lecture notes. Well, this is the whole lecture notes actually, not a sample. And you'll see there enough worked out examples. Go through them. Okay. How to find the derivative, first derivative and second derivative of a function like this. Okay. And these examples will help you understand how to solve the homework problems. Okay, so with that, let's start today's lecture. It's a review of vectors and matrices. It's not exactly a review, it's mostly a review, but I'll be adding some more things to it. Okay, so anyway, you guys definitely know how to multiply two matrices. The inner dimensions of the two matrices must be equal. This is a 4 by 5 matrix. So the inner dimension of this is 5, and this is 5 by 3. The outer dimensions are 4 and 3. The product will be a 4 by 3 matrix. And the inner dimensions must be equal. Okay, so this times this plus this times this times this plus this times this plus this times this. So first row, first column, that will give you this entry here, I1, 1. First row, second column gives you this. First row, third column gives you this. It's properly color-coded. And likewise, for the last, you take the last row and multiply it with the first column, second column, and third column of the second matrix, and you get these. Okay, so this is outline of today's lecture. Not all of them are things you know, but I think about 75% you know. And I assume that you know really rudimentary matrix operations and determinants. Okay, inverse of a matrix. A matrix, if you want to invert a matrix, the matrix must be a square matrix. The number of rows and columns must be the same. And furthermore, A must be a non-singular matrix. We'll get into that. Not all matrices can be inverted. The determinant of the matrix must be non-zero for you to be able to invert the matrix. Otherwise, the inverse of the matrix doesn't exist. So we assume that A is a non-singular matrix. Its determinant is non-zero. So A inverse A times A inverse equals I. I is the identity matrix. By identity matrix, I mean the diagonal elements of the matrix are 1, all ones, and the non-diagonal elements of the matrix are zeros. AB inverse equals B inverse A inverse. Don't ever write AB inverse equals A inverse B inverse. No. AB inverse will be B inverse A inverse. And it's the same thing for transposition, by the way. So AB transposed, when you swap the rows and columns, you will have to, when you expand this, if you remove this parenthesis, you should do B transpose A transpose. Determinant of a square matrix. The determinant of AB. Okay, you know basically what determinants are. The determinant of the product of two matrices, A and B, is, I'll follow either this notation or this notation. Both are equivalent. Okay, which is the determinant of the product is the product of the determinants. Determinant of A times determinant of B. We're dealing with square matrices, right? So A transpose, the determinant of this transposed matrix will be also equal to the determinant of the matrix. If you multiply a matrix with a scalar and the determinant, you'll have to change. Okay, determinant of alpha A is equal to alpha to the n, where n is the size of A, n rows and n columns. N by n is the size of A. Okay, so you will have to, when you take this scalar alpha out, you have to raise it to the power of n. The determinant of A inverse equals 1 over the determinant of A. This is a nice identity. The determinant of I, the identity matrix, plus AB transpose equals 1 plus A transpose B. One thing about the notation throughout this course, I'll use uppercase block for matrices. Lowercase bold, I mean bold. Uppercase bold for matrices, lowercase bold for vectors. And by default, a vector is a column vector. And non-bold italics for scalars. So this alpha is a scalar. N is a scalar. Okay. Okay, some more properties. Hermitian AH or A conjugate transpose. See, conjugate is when the elements of the matrix are complex, but we hardly deal with any complex matrices here. So for 99% of the cases, it would be just real matrices, in which case you can just ignore the star part. Okay, so A transpose, but if you have complex matrix, then you have to use this operation, A star transpose, conjugate all the elements, scalar elements of the matrix, and then you take the transpose. So this is what I said earlier, AB transpose is B transpose A transpose. We have to flip the order of the matrices when you're taking the transpose of that product. And likewise for this operation here. If it's a Hermitian matrix, then it's equal to AH. The matrix is equal to its conjugate transpose. Now, when we are looking at real matrices, if A transpose equals A, then we say that the matrix is symmetric. Trace of a square matrix, what we do is we just take a look at the sum up the diagonal elements of the matrix. This is an n by n matrix, so k equals 1 through n, a, k, k, a11, a22, a33, and so on. Properties of the trace. Trace of AB is equal to trace of BA provided, provided A and B are both of the square matrices of the same size. A transpose A is a scalar. You understand why A transpose A is always a scalar? See, any by vector, by default, will be a column vector. Okay. So when you take it, so let's say we have a 5 by 1 vector. Its transpose is 1 by 5, right? So A transpose is 1 by 5, oops, and A is 5 by 1. So when you multiply them, 1, 5, 5, 1, take the outer dimensions, 1 and 1, right? And so that's a scalar. Okay, and that's equal to the trace of AA transpose. AA transpose will be a matrix, 5 by 5. Okay, A transpose A is a scalar, and AA transpose is a matrix. Okay, remember that. And so these are the different, some of the other properties. And this is one property that sometimes comes in useful, the Woodbury formula. This is, let's do an example of how to solve matrix problems. Okay, suppose we have to prove this. This is an identity. Assuming that this is invertible, A is invertible, and A plus B C transpose is also invertible, then this identity holds. Why do I have 1 plus this in the denominator? Because it's a scalar. Both sides are matrices. The numerator of this term is a matrix, but it's divided by a scalar. You cannot divide a scalar or vector or a matrix by a vector or a matrix. Okay, so when you have something in the denominator, make sure that it's a scalar quantity. 1 is a scalar here. C transpose A inverse B is also, if you look at the dimensions, it will give you a scalar, this product. Okay? So let's prove it. The best way to prove it, since this is invertible, I'll pre-multiply both sides with A plus BC transpose. So what happens if I pre-multiply this side with A plus BC transpose, the product will be the identity matrix, correct? So this, on this side, I get this. On the right-hand side, when I pre-multiply it with A plus BC transpose, I get this. Okay, and this must be equal to the identity matrix, I. So let's try to simplify it. This pre-multiplication helps us remove this, take care of this inversion here. Otherwise, it will be hard to manipulate, right? A plus BC transpose inverse is not equal to, for instance, A inverse plus BC transpose inverse or something. No. Anyway, so we have this. Now let's open up the this side. So we have A plus BC transpose, A inverse, negative, this times this, which is equal to this. So I got this here. I open up this, and then when I open up this is what I get. Okay, so now let's go to the next slide. So this is what I have. AA inverse is I, right? AA inverse is the identity matrix. So that's I plus BC transpose A inverse negative of this. This denominator, you know, is a scalar. Otherwise, you cannot divide. Now, then what I do is I see there's B on the left-hand side of both. I bring it to this side. And then I see C transpose A inverse is on the right-hand side. You know, in a matrix product, the order of the individual matrices or vectors, whatever, have to be preserved, right? So this has to be taken out on this side. What's left inside? B and C transpose. This is 1 plus C transpose A inverse B. I took out B on this side and C transpose A inverse on this side. And so what remains is C transpose A inverse B C transpose. No, just A inverse B. Excuse me. So this is what I have. Okay. Now, I just told you that you must preserve the order of the matrices in a product, with the exception of a scalar. A scalar you can move around. Okay. So this, you see this is a scalar. So you can just bring it outside. Okay. That's the only exception. Otherwise, you have to preserve the order. So I just got it here. Now you see this is a scalar quantity within parentheses, and that's equal to what's in the denominator. Right? So what can I do? Scalar and scalar, the two are identical. We can cancel them out. What I'm left with is this, minus BC transpose A inverse, which is equal to I plus BC transpose A inverse minus BC transpose A inverse, which is equal to these two cancel out. I get the identity matrix. Hence, proved. So this is what we proved. Now, common mistakes. Okay. This is a wrong approach. So suppose, okay, we were arrived at this stage, that's fine, and then we try to simplify it this way. We see that, oh, we have BC transpose A inverse on both sides, here and here. So we take BC transpose A inverse, and then we have 1 plus BC transpose A inverse. This is absolutely wrong. Why? For one thing, 1 is a scalar. See, again, the purpose is, okay, somehow to match the numerator and denominator or whatever. But 1 is a scalar, but BC transpose A inverse is a matrix. Okay. So you cannot add 1 to a matrix. There's a size mismatch. Okay, so this is wrong. 1 is a scalar, but BC transpose A inverse is a matrix. Okay, let's try another way. We could have correctly factorized it. Instead of 1, I could have written I here. You see, A, B, let's say there are two matrices A and B. A, B is the same thing as A, I, B, which is I is the identity matrix, right? That acts as a 1. In scalars, it's like a 1. Okay, so that's a matrix version of a 1, the identity matrix. Okay, so when I took this, I can take this out, BC transpose A inverse, but instead of writing a 1 here, I can write an I. Okay, but then what happens? It leads to nowhere. What do I do next? This is a matrix, and this is a scalar. I cannot do any cancellations or anything. So this, unfortunately, although this step is correct, leads to nowhere. We cannot simplify any further. So when you solve these problems, you need to strategize properly. Norms of a vector. So this, by default, I told you, lowercase bold is a vector. And by default, it's a column vector, like this. So this is a column vector. These are the scalar elements. This is the LP norm of a vector. It gives you a scalar. Okay, so what I do is take the absolute values of all the scalar elements and to the power of p, add them all up, and then take the pth root. That is the definition of the LP norm. Okay? For instance, when p equals 1, I have something called the 1 norm, which is equal to this. I take all the scalar elements, absolute values of the scalar elements, add them up. That's the 1 norm of the matrix, of the vector X. Infinite norm is I take the maximum of all of these. You know the Euclidean norm. Euclidean norm is nothing but what we commonly know as the Euclidean distance. And if I don't have p specified in the subscript, then by default, you will assume that it's the L2 norm. And that's equal to, or Euclidean norm, it's equal to square root of x transpose x. Okay, and here's one of the properties. This is kind of common sense. You're taking the absolute values and taking the summing them all up, and then taking the pth root of that, you're left with a positive quantity always. So the LP norm of any vector is always greater than or equal to 0. LP norm of, when you add a scaling factor alpha, scale up all the elements of the vector by this quantity alpha, and then what happens to the LP norm? Basically, the LP norm also stretches by the same amount alpha. right? And you can easily see it with L2 norm. What happens, so you have a vector, what happens when you multiply the vector by 2, its length doubles, right? That's what it is. Triangle inequality. The sum of two vectors, the LP norm will be less than equal to the LP norm of x plus LP norm of y. Unit circles. Okay, so these are the loci of L1 norm, L2 norm, and L infinity norm. Okay, and their quote unquote radius of all these circles, the red, the green, and the blue circles, they're all 1. Do you understand what I'm talking about here? Okay. Inner product. The inner product is a scalar. It's in general, you have an inner product, but for us, since we are dealing with Euclidean spaces most of the time, all the time actually, the inner product is of these two vectors is x transpose y, which is the same as y transpose x. Why are the two equal? Because in general, the transpose of a matrix or a vector is not equal to itself, right? Because it's changing the rows and the columns. Well, a special case is the symmetric matrix. But in a scalar, if 5 is a scalar, what's 5 transpose? It's also 5, right? Now, x transpose y is a scalar, right? So what if I take the transpose of x transpose y? I'll have to flip them, right? Flip the order. So y comes first, y transpose, and then x transpose transpose, which is x. Okay. And you would have used this notation in physics, right? Physics or some other engineering subjects, and which is equal to, if these are two vectors, x and y, the inner product is the dot product, which is the Euclidean norm, or the length of x times the length of y times cosine of the angle between them. Projection. So I have two vectors, x and y. I want to find the projection of x along y. Okay. That's given by this. X transpose y, the length of the projection. This is x. So x transpose y is xy. You see this, right? X norm, y norm, cosine theta, right? What we need is simply x norm, L2 norm of x times cosine theta. So that's why I'm dividing x transpose y with the norm of y. So it's a scalar, the projection of x along the vector y. Okay? This is another inequality. The norm of x transpose y is less than equal to the norm of x times the norm of y. And that's evident because you have a cosine theta. The cosine theta cannot exceed 1. Matrix norms. Have you dealt with matrix norms? Yes. Oh, good. So, the definition of a matrix in general, so these are induced norms, okay? LP norm of matrix, so what we do is we take a unit vector x, and we can rotate, we can try all sorts of orientation of that unit vector x. And each time we see this a times x is also a vector, right? So which orientation of this unit vector x maximizes the length of the product ax? Okay, and that's the LP norm of this matrix A. We are restricted to X being a unit vector. Otherwise, we can remove that restriction, and what we do is we can adjust X, and then we can divide this with the L2 norm of, or LP norm of X. Same thing. So that's the norm of the matrix. Properties, it's similar to those of vector norms. Triangular inequality also holds. This is another useful identity. There's a more general version of this identity, actually. Forgot the name. Okay, now let's look at what is the L1 norm of a matrix and the L2 norm of a matrix. Okay, sorry, L1 norm and the L infinity norm of the matrices. Not L2, excuse me. This example will make it clear. So L1 norm of, this is the matrix. The L1 norm is we take the summation of J is fixed. We sum over I, rho. Okay, so we take the absolute values of the elements of each row I, sum them up separately. Okay, and then we'll see. So this summation, so what we get for here? This column. So there's the column, take the absolute values 2 plus 1 plus 2. Then for the second column, we have 4 plus 2 plus 1. For the third column, we have 3 plus 3 plus 1. Because we ignore the signs, we're taking the absolute values. And then we take the maximum of these three. This is 5, this is 7, this is 7. So we get 7 here. Infinite norm, we do the reverse. So we take the absolute values of each row and sum it all up. And then we extract the maximum. So 2 plus 4 plus 3 gives us this. 2 plus 4 plus 3. 1 plus 2 plus 3. 1 plus 2 plus 3. 2 plus 1 plus 1 is this. Gives us 9. Another useful norm is the Frobenius norm. So what we do is we pretend that the matrix actually it's a vector. And then we extract the L2 norm of the vector. That's the Frobenius norm. Okay, so this is the Frobenius norm of the matrix. We ignore the rows and columns, we pretend that the whole thing is a vector. Okay, and then we take the squares, absolute values, squares of all the individual elements, sum them all up together, and then take the square root. That's the Frobenius norm. It turns out that the Frobenius norm is also equal to square root of the trace of the matrix times its transpose. I'm ignoring the conjugate here, okay, because like I said, we are most of the time going to deal with the real matrices. Here's an example. So this is, well, not in this case, at least. This is the matrix A, and we want to find the Frobenius norm. So this is what we have, right? Let's use this expression here. So what we get is, we take the absolute value and square it, right? Each of the scalar elements. So 1, what's the absolute value times square of the absolute value of this? 1 plus j, its length is what? Square root of 2, right? Don't confuse this j, which is an index of a summation, and this j, which is the imaginary number. Okay, so 1 plus j, absolute value square is 2. Negative 2, absolute value square is 4. 0 square is 4, sorry, 0 square is 0, negative 1 square is 1, j, absolute value is 1, square of that is 1. And it turns out to be 3. So using this expression, we get 3 as the Frobenius norm. What if we do it this way? A transpose is this. We get this. You do the multiplication, we'll see, we get this. The trace is 7 plus 2, right? Add up the diagonal elements, absolute value of the diagonal elements, but in this case, they're all positive, so 7 and 2. And then you take the square root of that, which gives us 3. So the Frobenius norm of this same matrix turns out to be 3 if we use this expression here. Cool? Okay, now here's something that you might have dealt with, especially in communications, or you might have dealt with block matrices. Have you? So, block matrices. So here's an example of how to deal with these matrices. So you must, first of all, ensure that the rows and the columns have compatible dimensions. Okay, so this is a block matrix, and this is a block matrix. Okay, so we have to prove this. The good news is, once you ensure that the dimensions of the sizes of all the individual elements of the block matrix, each element of the block matrix is a matrix or a vector, right? So that they're all compatible in terms of their sizes, row-wise and column-wise, then you can handle them you can treat them just like you would treat scalars. Okay, except you need to preserve the order when you multiply. So A times I, so this is what we have to prove. So the left-hand side, let's start. So this is what I have. And then I take the product. A times I plus 0 times 0. Then A times A inverse B plus 0 times this big matrix, which 0 matrix times this will be 0 matrix, right? So you get 0 here. C times I plus I times 0, which is C times I plus 0. And then C times A inverse B plus I times this whole thing here. Okay, what's A times I? I is the identity matrix, so it's just A, right? And when you add 0 to it, the matrix of zeros, you still get A. So this is equal to A, this is equal to C, this is equal to A inverse is the identity matrix, right? And so it's I times B plus 0, which is B. This is C, and this, you see, C A inverse B, and then you have a negative C A inverse B. So they cancel out. All you're left with is D. So this is how you can handle a product of block matrices. Now a little bit of vector and vector calculus. Differentiation. Okay. So we have a function, but it's not a linear function. What this notation is, the Rn is a real vector of size n. Okay, so it's a function which accepts as arguments, as it's in its domain, n-dimensional vectors, real vectors, and then maps it to a real scalar as the codomain. Let's differentiate this. Okay, the derivative of such a function is called its gradient, and we can use either this notation or this notation. Now, since x is called a multivariate function, its argument is multivariate, multiple variables, or a vector. Okay, so this is the definition of the gradient. derivative of x with respect to x1, then x2, all the way until derivative with respect to xn. Hessian is the second derivative. So the gradient of this function, this is a scalar function, by the way. It's multivariate, but it gives you a scalar value. This is r, right? So del f of x is this gradient. This is a vector of this same size as x. Hessian of the same function is the second derivative. And it's like this. This is a square matrix. Second derivative of the function with respect to x1 squares, partial square f over partial x2 partial x1, all the way until partial square f over partial xn x1, and at the last bottom right is partial square f over partial xn square. Now this Hessian is always symmetric. Why is that? You see, the order of differentiation doesn't matter, right? So you can differentiate the function with respect to x1 and then with respect to x2, or you can differentiate the function with respect to x2 first and then with respect to x1, you'll get the same thing. Okay, so that's why all these, if take the upper triangular elements and the lower triangular elements, you'll get the same. That makes the Hessian of this matrix symmetric matrix. Simple case. So this is a bivariate function. F of x is, so it takes x1 and x2, two scalar variables, or a two-dimensional vector, size 2 vector. F of x is x1 squared sine x2 plus cosine of x1. So the derivative is, just differentiate this function with respect to x1 and then with respect to x2, and this is what you get. Now let's look at the Hessian. We got the gradient, Hessian. We can either double differentiate each of these, or we can take this and differentiate this. So we can do it this way, and this is, so we already got this, and then, so the first column here is we differentiate this gradient with respect to x1, and then second column we differentiate the gradient with respect to x2, and then what do we get? This. Is it correct? Oh yeah. Twice x1 sine x2. Sine x2 is a constant with respect to x1. So we get 2 sine x2, and this is negative sine. Derivative of the sine is the cosine. Cosine x2. x2 is a constant when we differentiate with respect to x1. So it's still cosine of x2, and this x1 square becomes twice x1. And likewise for the second column. Okay? Quadratic forms. So you have dealt with quadratic equations, maybe when you're in what? Grade 9, 10, something. At the very most, 11. But I'm sure before that. This is the vector matrix version of that. F of x, so we have multiple variables, x1, x2, x3, and so on. It's given by this, and these are the coefficients. This is a quadratic term, okay? And this is a linear term, summation pi xi. We can rewrite this in this manner, where q is equal to this. Okay. P transpose x is the same as x transpose p, remember that, right? The gradient is half q plus q transpose. Because Q might not be a symmetric matrix. So Q and Q transpose, you have to consider X. See, what's the scalar equivalent of this? Half QX square, right? This is P transpose X. The derivative, this is the linear term, first order term, P transpose X. Always remember when you do this differentiation, the derivative, the gradient has to be a column vector. P transpose is a row vector, right? So you have to take the transpose, so it's a column vector. And the Hessian is simply half of Q plus Q transpose. Now, 99% of the cases, in real world and any application, Q will be a symmetric matrix. Okay. In which case, when Q is symmetric, then what happens? Q and Q transpose are the same, right? Q transpose equals Q. So this reduces, the gradient reduces to half of Q plus Q is Q, right? So QX plus P, this is the gradient. And the Hessian becomes Q. Always remember this, okay? If you're given a quadratic expression like this, then the first derivative is this, and the second derivative is this. And now what happens is, why do I assume that Q is symmetric? Because if suppose you're given a Q that's not symmetric, okay, you can replace this Q with half of Q plus Q transpose, and you'll get the same value. Okay. So I have written something like that in the lecture notes. Q sim and Q skew symmetric. Q minus Q transpose is a skew symmetric matrix. Okay, just go through that and you'll understand. It's very simple. Okay, so quadratic form, just memorize this. Okay, it's easy. Okay, differentiating quadratic function. So this is, we're given this, and if we simplify it, we get this function. This is a scalar form. Okay, this is the same formula in terms of matrices and vectors. So this is, f of x is, this is Q, this matrix that I've colored red, and this is P, or P transpose since it's a row vector. Okay, so we can take the derivative like this. We can just differentiate this, and we get this. Take the derivative with respect to x1, you get twice x1 plus x2 is fixed, right? So derivative of a constant times x1 is x2, this constant, and 3 over 2, x2 square is 0 when we're differentiating with respect to x1, right? And then you get a 3 here, and likewise for the second row. Okay, so you get the gradient directly from this. Otherwise, you can use this expression. What's the gradient of this? Q is symmetric. You can see that Q is symmetric. Q 2, 1, 1, 3. It's symmetric, right? 1 and 1. Excuse me. So you get, if you use this expression, it's QX plus P. That's exactly what you get. And del square F is Q. You can either take the second derivatives and fill out these 4 scalar values. Otherwise, you can simply use this expression here, Q. Okay, block quadratic form example. Let's find del F and del square F. We are given this. what we can do is simplify it, right? You get this. For I take, you understand the associative property of matrix multiplication. So you can either multiply this matrix and this matrix first, and then multiply the product with this matrix, or you can multiply this and this first, which is what I've chosen to do. So AA transpose X plus identity matrix times X is X. And then here I have 0x is 0 minus identity matrix X, you get negative X. And then multiply it with X transpose, this is what you get. Okay, so this is X transpose, AA transpose X is what it simplifies to. AA transpose is always a symmetric matrix. A matrix, the product of a matrix and its transpose is always a symmetric matrix. For obvious reasons. You can see here. A transpose, you take the transpose of the product of A and A transpose, you get this, which again is AA transpose. So obviously AA transpose is symmetric. Okay, so it's this. X transpose QX. What's the derivative of X transpose QX? Twice QX. Right? If I had a half here, then it would have been QX, but I don't see a half here, so it's two times, right? Derivative of half X transpose QX when Q is symmetric would be QX, right? So here it will be twice QX, or twice AA transpose X, and the second derivative will be twice AAQ, which is twice AA transpose. Euclidean norm. Okay, so we're going to find the derivative of the L2 norm of a vector and 1 over the L2 norm of the vector. And we'll use these expressions. You know, X transpose X, you can always insert an identity matrix inside. It's like X transpose QX, where Q is I, the identity matrix. Okay, so same expression as this, where Q is the identity matrix. What time is it? Oh, we still have time. I'm looking at that clock. Okay, so back here, the L2 norm is simply this, X transpose X, square root of that. So the derivative of this is 1 over 2, you know the expression for the square root, right? And derivative of times the derivative of X transpose X, 2X. And likewise, the derivative of 1 over X is, I should have a negative sign here, right? I should have a negative sign here. Derivative of 1 over X is negative 1 over X squared. So, and then, so 1 over L2 norm squared times the derivative of the L2 norm itself, which is this. So I forgot to write down the negative sign here. We'll try to work it out because it's there in the homework. Here's another algebraic example. This will be the last one. We'll differentiate this. A transpose X, X transpose, we'll have to, we have to differentiate. A transpose X, X transpose B. A, X, and B are of identical sizes. They're vectors of the same size. And we have to show this. Method 1, we'll use this expression. Derivative of x transpose qx is q plus q transpose x. Okay, so now what I do is, before I take the derivative, I group, I apply the associative property, so I can take the products any way I like. A transpose x I group into one, and x transpose b I group into the other. Now note that both A transpose x and x transpose b are scalars. Okay, and then what I do is, since they're scalars, I'm free to take transposes, right? So I can freely take the transpose of this and the transpose of this separately, and I get A transpose. The second one, there should be a. Never mind. So this is A transpose x. I take the transpose of that, and I get x transpose A. And likewise, this one, I take the transpose of x transpose b, I get b transpose x. Since they're scalars, you're free to take the scalars. So I get this. What this trick accomplished is I took the x's outside. So it's of this form. And inside, what you have inside is a matrix. Okay, and now I'm free to take the derivative, to apply this expression here, this identity, to take the gradient. So derivative of this, what's AB transpose here? It's playing the role of Q. So take the derivative, I get this is Q, AB transpose, and this is AB transpose transposed, right? Times X. This X is this X, which is equal to this. AB transpose plus BA transpose times X. Okay? The other way to do this would be use this. This is the derivative of the product of two functions, is first function times the derivative of the second plus second function times the derivative of the first. So I group them as before, and so it's the product of two functions. First function times derivative of the second plus second function times derivative of the first. What's the derivative of B transpose X? B. What's the derivative of A transpose X? A. And since A transpose X and B transpose X, they're all scalars, I can manipulate them. So this is B times A transpose X. I take this B transpose X to the right and this A transpose X to the right of the first term. So I get this. And then I remove the parenthesis. I get this. I take X common outside. This is what I get. Same thing, right? So there are two ways to solve the same problem. Any questions you have? This lecture was fairly simple, right? So we have roughly 8-9 minutes left. Anything that I need to expand a little bit on? Any explanation?
I've got a curiosity question. It's not at all relevant, but flip to the slide with the quadratic form. Yeah. So this is the matrix expansion of x squared. What would the matrix expansion for x cubed be? Just out of curiosity.
It would be a tensor.
It would be a tensor?
Yeah. So it's a three-dimensional array. Now, in matrix analysis, normally we refer to the size of the matrix as the dimensionality. So the dimension of the vector is 5. Okay, But I sometimes call it the dimension, but I prefer to call it size because in tensor algebra, the word dimension refers to something else. So this is a two-dimensional tensor. You can also have a three-dimensional tensor. Okay, so when we do Taylor series expansion, when we go to optimization, so take a nonlinear function and then you have a Taylor series expansion. We will always ignore the third derivatives. Just restrict our attention up to the second derivative point. Okay, because third derivative will complicate things. But anyway, this is, does this answer your question?
Yeah, I was just kind of curious.
Yeah. And again, since we're in this slide, note that if you have a matrix here, Q, that's not symmetric, okay, you can take the symmetric version of the matrix, Q plus Q transpose divided by 2, and then plug it in here. You'll get this term will be the same. What else? We will do rank in the next lecture, but I'm sure that you guys understand exactly what rank of a matrix is. This is just not in the course, but does anyone wonder what happens to what's the zero norm of a vector?
Isn't it like the axes or something?
No.
No.
The zero norm of the vector, you're given a long string of values, is the number of non-zero scalar elements in it. So the quote-unquote circle would be just this cross. Okay. And half L half norm would be something like this. It would be like this. Sorry, I can't draw, but it would be something like this. Okay. I hope you guys have fun in this course. You'll enjoy it. Anything else? Be careful about these, how to handle these, okay? And never make these kind of mistakes. You can never do this. So you have one is a scalar and a BC transpose A inverse is a matrix. This is absolutely like level 0 error. It's pure ignorance. Okay, I actually do severely penalize those, by the way. And likewise, you cannot, if this were a matrix or a vector, the denominator, you cannot do that. That's an invalid operation, right? Okay. Now, since we have at least 5 minutes, why don't we look at the homework? The first homework, I gave you oh no, oh, that's what happened. So, reference sheet part A, this is something that you might find useful. Oh, asymmetric is half Q plus Q transpose. A skew symmetric is half Q minus Q transpose. What's a skew symmetric matrix? Oh, this is A and A transpose. This is A and A transpose, not Q. Sorry about that. Okay. Skew symmetric matrices, if you take the transpose of the matrix, you will get the negative of the matrix. That's a skew symmetric matrix. And so these are something, so we'll do these later on. And so we have done some of these. You'll see all the expressions here. I will add stuff to it, specifically for this course. Okay, I'll do some replacements and add stuff to this. Now, go back to the, let's take a look at the homework. So this, and by the way, if you go to files, in student, if you go to files, notes, yeah, Word documents, you'll actually get the Word equivalent, Word documents. And you can actually edit it as per your convenience. Okay, so that it's a quick reference for you when you solve problems, especially during the quiz. And you have my lecture notes too, and the slides. So the way you can address the homework is you can copy paste from those. And we have the questions also in MS Word. All the Word versions are all available to you. So you can easily copy paste. So this is the first homework. It doesn't have any MATLAB, so that's because I'm giving a little more time for the distance students to familiarize themselves with, so let's, what did I do? No. So these are, now what I do is there's 15 points, right? I grade, so 15 points, I'll grade them out of 30. Okay, so what you'll see, everything will be double. The quizzes are worth what, 8 points each quiz? So you'll have 16 multiple choice questions or fill in the blanks. Okay, so and everything, your total score will be out of 200. So you have to, so these are, I think we did this, some other version of this as an example in the class. And this too, a more complicated version of this we solved in class, right? We have to prove this. These are much simpler ones. Derivatives, I haven't gone through this. So does it seem to be, it seems to be quite fairly straightforward. Compute the inverse of the block matrix IA0 minus I. You assume that the inverse is of the form WXYZ. We don't know the values of WXYZ. And then you either pre-multiply or post-multiply. And then you pre-multiply or post-multiply by this, and you solve for W, X, Y, and Z. Here, non-singular matrix, sure, the following block matrix also. If P is non-singular, obviously because P inverse exists, right? It's non-singular. We have to show that this block matrix is also non-singular. So create a block vector XY. And then you solve. In the next lecture, I'll address how to solve this. Okay, it's actually quite straightforward, but it's just calculus and matrix algebra, undergraduate level linear algebra. That's all. I would prefer that you don't, but you can. It's quite, actually, when I do derivations for my research, I just copy paste. I do all the derivations in Microsoft Word or LaTeX. Actually, I prefer Microsoft Word. I'm more familiar with that Word because you can easily copy paste. So everything reduces to copy paste. That's why. And PowerPoint, you can also copy paste into Microsoft Word. So it's a lot easier actually than writing for me. If you just take a little, it just takes a little practice, and you'll find it useful for other courses too, and for your thesis or dissertation when you write that.